All right. So you took some time there to try to come up with a phase portrait for this system based on drawing null lines. The null lines, as I mentioned, are pretty simple. The x null lines are y equals 0 and plus or minus 1. They're going to be 3 horizontal lines. And the y null line is going to be at x equals plus or minus 1. Those are 2 vertical lines. So those 3 horizontal lines and 2 vertical lines will cross at 6 equilibrium points. And then the hard part is drawing the rest from there. You can cross the null lines correctly, but there are some subtleties. However, it's with this particular kind of system, it is good to try to do something else besides just draw null lines. You think you know what I'm hinting at when I say that? Looking at the system? Here's another letter that might be a hint. H. What does H represent? Hamiltonian. Yeah. I wrote the right and right sides here as f of xy and g of xy, though it is also true that f only depends on y and g only depends on x. Whenever that happens, whenever dx dt equals something that only involves y, and dy dt equals something that only involves x, when they're nice functions, which these are, that will be a Hamiltonian system. The right-hand side of the dx dt equation will be the partial derivative of some function with respect to y. And the right-hand side of the dy dt equation can be thought of as the opposite of that same function's derivative with respect to x. If we wanted to confirm that this is truly Hamiltonian with the condition that could have come up on the test for Hamiltonian systems, and did it? I forgot if it came up for Hamiltonian or gradient. One of those two it came up on the test. We need to check, does the derivative of f with respect to, careful, with respect to x always equal the derivative of g with respect to y, or the opposite, excuse me, of that? Well, f doesn't really depend on x, so its partial derivative with respect to x is always 0. The partial of g with respect to y, since g doesn't really depend on y, is also always 0, including with the negative sign. These are equal, and they're both equal to 0 for all points x comma y. That's enough to say that the condition for being a Hamiltonian system is met, and there is some Hamiltonian function. We'll graph it in Mathematica. And moreover, what was the other important point about Hamiltonian systems in relationship to their level curves? Solutions lie on top of the level curves. And what that's going to imply, and this is related to a subtlety with your drawing, is there's actually no way any equilibrium point can be a spiral, sink, or source, or in fact, even a sink or a source at all, it turns out. The equilibrium points when they are hyperbolic, non-degenerate, will have to either be a saddle point or a center. And actually centers are not hyperbolic, but those are the two things that can happen for equilibrium points in non-degenerate cases, is you either get a saddle point or a center with ovals around the equilibrium point. Because that's how level curves have to connect up, typically as ovals, when you're near equilibrium points at least. But how do you find the Hamiltonian function? Well, these right-hand sides are derivatives of the Hamiltonian function, so you just need to integrate to find it. Integrate this first one with respect to y, because it's supposed to be the derivative of the Hamiltonian function with respect to y. I could write h of xy is an integral of f of xy with respect to y. I know it's Hamiltonian, so this has got to be true. F has to be partial derivative of h with respect to y, and therefore, if we integrate it with respect to y, we should get h. However, it is still a little tricky to think about because what about the x? What do you do with the x? F, in its first form, has formula negative 4y plus 4y cubed. There's no x there. How is this thing ultimately also going to depend on x? That's a little bit of a mystery. Go ahead and do the integral. Integral of negative 4y is going to be negative 2y squared. Integral of 4y cubed is going to be plus 4y to the fourth. Plus c, should I write a c? You could, but realize for the purposes of this integral, that constant of integration really could depend on x, because for the purposes of this integral, x is fixed. There is no x there. There's an x there. Ultimately, because we want this to be true as well, and we want h to be a function of two variables, I do want a quote unquote constant that depends on x. What should I call it? I could call it c of x. Somewhat traditional to call it, say, phi of x or psi of x, but this is not a flow. It's a constant, you might say, but that constant depends on x. It's a constant with respect to y. I want the negative partial derivative of this with respect to x to equal g. I want this to be true. So the question is, how do you choose this function to make that happen? Well, the opposite of the derivative of this with respect to x is the opposite of the derivative of this phi function with respect to x. And g, going back up here, has this formula, negative 3 plus 3x squared. This is negative 3 plus 3x squared. So in other words, this means ultimately, if I multiply both sides by negative 1, phi prime of x is 3 minus 3x squared. So phi of x is the integral of 3 minus 3x squared with respect to x. And that gives 3x minus x cubed plus c, say. However, with Hamiltonian functions, unless it truly represents something physical like total energy, the c really can be anything. And so you might as well take c to be 0. Say that again. Unless the Hamiltonian represents something specific like total energy, you can take c to be 0. Although there's a caveat there as well. I mean, potential energies theoretically can be determined up to additive constants as well. And so when I say this is H is the total energy, I really could add constants to that as well, because potential energy has flexibility, you might say. Don't worry about that if that doesn't make much sense to you, because it's not really a big deal. So in the end, I'm going to take c to be 0 and combine these two facts, this fact right here plus this fact right here, to say that h of xy is negative 2y squared plus y to the fourth plus 3x minus x cubed. And again, I'm taking the c to be 0. Those two facts will combine to say this. So now if I can use technology to draw the level curves of this h function, curves on which it is constant, those will be the same as the solution curves. So the solution curves also have a direction of motion, an arrow along them. You can, before I make the contour plot, let me also emphasize that you can draw the ordinary graph of this Hamiltonian function. And here it is, I plugged it into Mathematica, that is the same thing. There's an ordinary graph of it. If you're in multivariable calculus, you've seen these kinds of graphs before. Think of the xy plane as being horizontal, the x-axis going to the right, the y-axis going into the screen, and a third axis, z-axis, going upward. You plot this function by plotting three-dimensional points, x, y, z, satisfying h of x, y equals z for different values of x and y. For example, when x is 2 and y is 1, z is -3. When x is 2, when you're over here on the right, and y is 1, basically right above this point here, the z coordinate is -3. Can we see that? It's hard to tell for sure, but 0 is above the bottom of the box there. So yeah, this point right around in here is below 0. So fully oval. What are level curves? Level curves are created by slicing this graph with horizontal planes, different horizontal planes, to get curves on which the function is constant, and here they are. And for the Hamiltonian system, the system of differential equations, the solutions have to be on top of these level curves. So if you made drawings like these kinds of curves, then you were accurate. You do have some periodic solutions that come back to where they start over here. Also, some that go around some equilibrium points over here. You also have so you got 6 equilibrium points, 3 along the line x equals -1, and 3 along the line x equals +1. The ones over here, and here are going to be centers. The one here is going to be a saddle point. Over here, it's the opposite. The one in the middle is a center, and the opposite two are saddle points. Let's show the stream plot on top of this to confirm that. What is it the stream plot of? A certain vector field. It's this vector field here. Here. That vector field here. Right? That first thing, -4y plus 4y cubed, is little f, and the second thing, -3 plus 3x squared, is little g. Copy and paste that in here. And there they are. You can plot the equilibrium points as well. This plot is one way to do that. There's 6 of them. -1, -1, -1, 0, -1, 1, +1, -1, +1, 0, and +1, 1. If you happen to find the equilibrium points, those are the things you should have gotten. There they are. With linearization, with the Jacobian matrix, confirm the nature of these equilibrium points? Yes, though with a bit of a caveat. The ones that are the centers, the Jacobian matrix is actually going to have purely imaginary eigenvalues, which is actually the case where the Hartman-Grobman theorem doesn't apply. And so technically speaking, though we can linearize, we're not linearizing in the usual way. We do need to rely on the fact that the system is also Hamiltonian to know that those solution curves are on top of the level curves. The Jacobian matrix, in this case, I like typing in like this here. Type. The f of x, y, I think I didn't define f and y though. F really, again, only depends on y, but I'll put an x in there anyway. G only depends on x, but I'll put a y in there anyway. And this is really f of x comma g of x. Same picture. I'm trying to make the Jacobian matrix now, so I'm taking the first row to be the derivatives of f with respect to x and y. Second row to be the derivatives of g with respect to x and y. And if I want to plug in a specific point with coordinates x0, y0, technically I need to do this little trick here. There's the way of doing that. And so now I can linearize, certainly at the saddle points, linearization applies. The Hartman-Grobman theorem. One saddle point is -1, 0. Trace's 0 determinant is -24. The determinant being negative in the trace determinant plane means you're below the trace axis. That's where saddle points occur. And that is hyperbolic. The eigenvalues, one is positive, one is negative. One's positive, one's negative. In fact, they're opposites of each other even. That's happening by the symmetry involved. You actually can use this to also help you draw the solution curves near the equilibrium points, because the eigenvectors, while they're not on straight line solutions, they are on solutions separatrices that are close to being straight near the equilibrium points. I'm talking about solution that would come in. Let me get rid of the shading here. I'm talking about this equilibrium point here. There'd be what you might call a stable separatrix, a solution that heads towards that as t goes to infinity, coming in about like this, and another one from down here coming in about like this. And actually, it's kind of interesting, those two solutions, if you follow them backwards in time, like watch the cursor here again, forwards in time means you're going down this way toward the equilibrium point, but if you let t decrease, let time run backwards, it actually also has to be the separatrix that is a source in the other direction, because you're going to have to come back to where you started because it's Hamiltonian. Turns out it's going to have to come back to where it started. Same kind of thing over here. A solution approaching this point as t goes to plus infinity is going to approach it also as t goes to minus infinity, coming back this way. That doesn't typically happen, but it's happening for Hamiltonian systems. These two would be saddle points as well. Let's pick on one of the centers here, like at +1, 0. The matrix has trace of 0. Determinant is positive, though, +24. 0 minus -24 is +24. And in the trace determinant plane, that means you're on the positive d axis, and that's where centers occur for linear systems. This linearized system would be a center. So in that sense, it's not surprising that these things are centers. However, again, that Hartman-Grobman theorem only applies when your eigenvalues are not purely imaginary and they're also not 0. So technically speaking, even though you can say they're centers, you're not truly applying the Hartman-Grobman theorem in that case. Okay, so it's a pretty picture. For the same function h, I could also make the corresponding gradient system. I haven't written it down yet. I didn't give you a system to begin with and said, is this gradient or not? But I could find it for gradient system, for the corresponding gradient system. And these Hamiltonian systems and gradient systems always, in 2 dimensions at least, go together. If you got a Hamiltonian system, you can always write down the corresponding gradient system and vice versa. A gradient system has the form dx dt is the partial of some function with respect to x, not y. And dy dt is the partial of some function with respect to y, not the negative of that same function with respect to x. What you call the function is irrelevant. I'm going to use the same h function, so I'm going to call it h here. However, it's not going to be a Hamiltonian system. So maybe I should use a different letter besides h. A common letter to use is v. because V is also a common letter used for potential energy, which can get dissipated with friction. Gradient systems, friction can occur. Partial of this with respect to x is 3 minus 3x squared. Partial of this with respect to y is negative 4y plus 4y cubed. The right-hand side of the dy dt equation is the same as the right-hand side of the dx dt equation for the Hamiltonian system. And the right-hand side of the dx dt equation, 3 minus 3x squared, is the opposite of the right-hand side of the dy dt equation for the Hamiltonian system. So all I did here was I swapped the components of the vector field and negated the first one to get back to a positive partial of h with respect to x. And because you swap that and swap those and negated one of them, as vector fields, they have to be orthogonal to each other. Anytime, you notice if you write these as vector fields, capital F has components little f, little g for the Hamiltonian system. Let me call this capital F sub ham for Hamiltonian. It's supposed to be an H-A-M, ham. Ham for Hamiltonian. The corresponding vector field down here, which is for a gradient system, F sub grad, say, if I use the same letters, little f and little g, as I used before, this really becomes negative g f, if I'm using the same letters as before. And I know it's a little confusing. Usually we always call the first component f and the second component g. And I'm doing that for the Hamiltonian system. What I'm trying to get across here is if I convert this Hamiltonian system to the corresponding gradient system and use the same letters for the same functions, little f and little g, which are these two functions, then I have to switch them around and negate the first one. And these are conjugate. F ham, now conjugate is a word to use, they're also orthogonal. Dot f grad, dot product, is this vector dotted with this vector. And that's negative fg minus fg is always 0. Notice there's no x's and y's there, but that's implicit. This is true for all points x, y. It's implicit that these things depend on x and y. So again, the vector fields, when you plot them at any particular point, those two vectors that are plotted, one for the Hamiltonian system and one for the gradient system, have to be perpendicular to each other because the dot product is always 0. And since the Hamiltonian solution curves have to lie in the level curves of H, that means the gradient system for that same H has to have curves that cross the level curves of H orthogonally, normal to them, in other words. So let's go ahead and have the computer do it here. So I got the same F and the same G, but for the gradient system, I have to switch them around and negate the G. I'm still going to have the same equilibrium points, right? The null lines are still going to be the same lines, although which null lines go with which lines changes. Up here, the x null line was where f was 0, which is horizontal lines, y equals 0 and plus or minus 1. Those three horizontal lines are where you cross vertically. And the y null line is at y equals plus or minus 1. Those are vertical lines at x equals plus or minus 1 where you cross horizontally. The x noclines for this one become the y noclines for the gradient, and the y noclines for this one become the x noclines for the gradient system. What does it look like? Now it looks like this. You're crossing the level curves of H orthogonally. You could also use the word normal, or you could also use the word perpendicular. And with gradient systems, you're never going to get centers. Yeah, you'll never get centers, but you could get sinks, sources, and saddles. For the Hamiltonian system, the centers become sinks and sources. These two are sources over here, and this one's a sink. And the saddle points for the Hamiltonian system become also saddle points for the gradient system. In this case, linearization, Hartman-Grobman theorem would apply to all the equilibrium points. If I do the Jacobian matrix in this context, it means I need to change the f's to g's and put negative signs in front of the g derivatives. Because I'm switching around the components of the vector field, change the g's to f's. Now, if I do these, the linearization, for example, at the point -1, 0, I can see in the graph it says it's a saddle point. This should have one positive, one negative eigenvalue. Its determinant should be negative, which it is. And at 1, 0, you can see that one's a sink, not spiral. You don't get spiral sinks or spiral sources. You're going to get real sinks and real sources. So you never get centers for gradients. You never get spiral sinks or spiral sources. You can get real sinks and real sources and saddle points. This one's supposed to be a source. We should get, no, that's a sink, excuse me, right here. So the eigenvalues should both be negative. The determinant should be positive and the trace should be negative for a sink. Trace is negative, -10, determinant's positive 24. The eigen system here has two negative eigenvalues. The corresponding eigenvectors are horizontal and vertical. You actually do have straight line solutions here. That's not typical for nonlinear systems. The noclines are actually straight line solutions. You're not truly crossing them. Like this nocline at x = 1, this vertical line here, is an x nocline. The vector field was vertical along it. But because the line itself is vertical, that means you got straight line solutions on it. Okay, same over here. Same with these horizontal noclines as well. So one thing about this stuff is it is kind of interesting, I think. Another thing is it does have applications. Hamiltonian systems arise when mechanical energy is conserved. Gradient systems arise with friction. Problems with friction, they're not all problems with friction. Can I clarify anything? It's possible the system could be Hamiltonian and both the dt and dy/dt equations could involve both x and y. That could have happened. Let's do a quick example in Mathematica where that happens as quick as we can here. So this will be example 1 here. Hamiltonian and gradient. Example 2. Let's change the Hamiltonian function slightly for the Hamiltonian version. Let's make it have a term that involves both x and y, say x times y. Now the partial of h with respect to y will include x, and the partial with respect to x will include y, because you got this plus x times y term. If you differentiate that with respect to y, you get x. If you differentiate it with respect to x, you get y. Since I'm adding this thing that doesn't, I'm not sure how much it's going to affect the graph. It didn't change it too much. And if I put it like a small number in front of it, it would change it even less. This is, maybe I should do that. Got a small number in front of x times y. It doesn't, it's not much different from the original graph. Here's the original graph. If I add a small constant times x times y, it's not going to change the graph much near the origin. It doesn't look like much of a different graph. If you go further away from the origin, the change is more significant. But I'm still interested in the corresponding Hamiltonian system. But now both right-hand sides depend on both variables. If I want to graph it with ContourPlot and StreamPlot, I just need to make these modifications to F and G. The ContourPlot's not going to change a ton, and the equilibrium point's not going to change a ton. There still probably are going to be six equilibrium points, not too far away from these. I better not plot these points though, because that would be confusing. Those will no longer be equilibrium points. I mean, I could, you'll see that they're not exactly where the true equilibrium points are. I mean, for example, this one's not centered right in the middle there. They're close to the equilibrium points, but they're not exactly on top of them. Finding the exact equilibrium points is probably pretty difficult. You have to use some numerical method to approximate them. I'm going to get rid of the list plot here. There are still six equilibrium points. They're just not exactly the same as before. Since you'd have to approximate the equilibrium points, when you linearize, you'd have to approximate them as well. It is still Hamiltonian, so the solutions are still on top of the level curves. The level curves change just slightly. If I change this to a 1 instead of a 0.1, they change a bit more. Now the level curves changed a bit more. But why is the stream plot not right? Oh, that's okay. The stream plot was correct because I changed F and G, but I didn't change H. Let's go back to changing these to a 1 here. Now these. I still have 6 equilibrium points here, but you'd have to approximate them. You could still linearize, you could still try the Jacobian matrix, but you'd have to plug in the approximate equilibrium points. The null lines are no longer horizontal and vertical. Could I graph them? Sure. Do ContourPlot again here. F of xy equals 0, g of xy equals 0. Those are going to be the null lines. They're no longer going to be horizontal and vertical, but maybe not too far from horizontal and vertical. The brown one's not too far from vertical. The green one's a bit more far from vertical. Those are the new null lines. They do go to the equilibrium points. The system still is Hamiltonian, so the solution curves are still on top of the Hamiltonian functions level curves. I can do the same kind of thing with the gradient system. And get rid of those equilibrium points that are no longer equilibrium points. There's the new gradient system for the new Hamiltonian function. Okay. So not talking about applications. The applications are in the book. The most famous application is the pendulum. But you can generalize to the double pendulum and things like that as well. But then you're going to do a higher dimensional phase space, like a 4-dimensional phase space, and you can't visualize things nearly so nicely. For our last bit of time today, I'd like to get you out a little early, but I'd like to do one more example of something. Let's do a linear algebra topic, quadratic forms. So quadratic forms, learned a little bit about in the lectures, are functions. They're quadratic functions, in fact. And you can represent them using matrices in a special way. And I'd like to create a quadratic form, let us say positive definite. Here's how I'd go about creating one. Say for a test question or something. I'd start with a diagonal matrix, call it D, that has positive numbers in the main diagonal, say 2 and 3. I'd like to transform this matrix D to a non-diagonal matrix that is still symmetric. So I want to make a P matrix. And if I want to make sure the transform matrix, call it A, is symmetric, I want to choose P so that its inverse is its transpose. So this is like orthogonal diagonalization, but I'm going in the opposite direction, right? Usually we start with the A matrix and we figure out the D matrix. Now I'm going backwards. I'm starting with the D matrix and trying to figure out the A matrix. If P is going to orthogonally diagonalize, I better have orthonormal columns. It's called an orthogonal matrix, not an orthonormal matrix. Unfortunate, it'd be better to call it an orthonormal matrix. Here's one example that's easy to remember. If you choose columns that look like that, for example, that'll be an orthogonal matrix. I'm going to let A be the inverse of P, which is its transpose. I'll type it as transpose P, times, no, it's the other way around. P times D times the inverse of P, which again, since P is orthogonal, is its transpose. So A should be a non-diagonal matrix. We're going to have non-zero off-diagonal entries, but it should be symmetric. It is. So this is going to be my matrix from the quadratic form I'm trying to create. How do you actually create the quadratic form now? You start with an arbitrary row vector, xy, multiply that by the 2 by 2 matrix A, and then multiply by the corresponding column vector xy. If you do this product, think about it with me here. We've got this row vector is, as a matrix, that's a 1 by 2 matrix. Times a 2 by 2 matrix is going to be a 1 by 2 matrix, a row vector. And a 1 by 2 matrix times a 2 by 1 matrix is a 1 by 1 matrix. You then had 1 by 2 times 2 by 1. It's really a dot product. This is going to be a number written as a matrix. Written as a 1 by 1 matrix. 1 row, 1 column. And that number, since it involves x and y, can be thought of as a function. Call it q of xy. It's a function of 2 variables. And it is a quadratic form. Each term, in a sense, is a quadratic. You've got an x squared term, and a y squared term, and a cross term, x times y, which you can think of as a quadratic because you imagine adding the powers to say this is still degree 2. I could make a contour plot of this. This is a multivariable calculus function. And because I started with a matrix whose eigenvalues are both positive, the eigenvalues of A are going to be positive as well. In fact, they'll be the same eigenvalues, 2 and 3. And that's enough to say that even though this quadratic form has a negative coefficient here, it's still going to be positive definite, and it will never take on negative values. All these level curves have positive outputs, never negative. And that's why it's positive definite. Positive definite means the output of Q is always positive when you don't plug in the origin. When you plug in the origin, it's 0. But otherwise, it's always positive. So we call it positive definite. And I knew that had to happen in spite of the minus sign here, because I started with a matrix whose eigenvalues were positive, and therefore the A transform matrix also has to have the same eigenvalues. They're both positive still. I knew I had to get a positive definite quadratic form. All right, that's this example 1. Let's quickly do examples 2 and 3, where we just modify this. If instead I had started with a matrix, both of whose eigenvalues are negative, like this, then the A matrix would also have the same negative eigenvalues. This would be a different formula. In fact, it's the opposite of the previous one. That's a negative definite quadratic form. And the level curves always give you negative outputs. Example 3, example 2. Example 3 will have one positive, one negative eigenvalue. Positive 2 and negative 3, say. Now A again has the same eigenvalues. One positive, one negative. The formula ends up having a mixture of positive and negatives, but this one is not positive definite and it's not negative definite either. It's called indefinite. It takes on both positive and negative values. Positive up here and down here. Negative here and here. Okay, so the point about bringing up quadratic forms, in part, is that it's another application of eigenvalues and diagonalization. You can think about these functions in any class. We're applying linear algebra to it. So you can think of it as a linear algebra class, but we also could bring differential equations into play with this stuff if we wanted to. We could think about the corresponding gradient in Hamiltonian systems for Q. Q could be a Hamiltonian function for a Hamiltonian system. It could also be a potential function for a gradient system. The H or the Q or the V, whatever you want to call it, for a gradient system, it's called a potential function because it often represents potential energy. Now, I've done enough here that I'll save this Mathematica file and send it to you after class today. But we'll end early. Have a good day. I'll get the